In Part 2, we will look at the Calculate Branch Diameters feature and discuss special nodes to represent household connections and use those with extended period simulations. With the Calculate Branch Diameters analysis, the modeler can calculate the design flow, size pipes, and apply these to create an updated model. This feature requires that household connections are represented using residential meters. This is our example from previously, which uses residential meters. We are assuming at this point that the number of connections, elevations, and overall layout are input, and that the assumed initial pipe data, diameter and roughness at least, have been input, and that the model can be successfully analyzed, but the results may not be what is desired. First, you will need to decide on the method you wish to calculate the peak flow. There are two methods. We can take the average consumption in gallons per day or liters per day and input a peak factor, or we can input A and B coefficients. Presumably, your decision would be based on your regional regulatory requirements. We bring up the Analysis Setup menu, select Calculate Branch Diameters, and launch the analysis. Here are the inputs for the tool. As you can see, the two calculation methods can be selected at the top. Below, you can select a pipe schedule or load one from the pipe type table or one you've previously created. You can specify an overall minimum diameter allowable for the simulation, a minimum velocity, and a maximum velocity. We'll apply these defaults and run the analysis. We can apply the new diameters from the analysis to the pipes. Let's run the analysis to see what the pressures and flows are. By running the analysis in this case, I mean running a steady state KY pipe analysis with the new pipe diameters. And we'll also review the new pipe diameters. We can click on individual pipes and see that previously this was a 2-inch pipe. It's now been assigned a 1.5. These in the loop have also been assigned a 1.5. And this, previously a 3-inch diameter, is now a 2-inch. We've rerun the analysis. Let's display our velocity labels. This is another shortcut way to turn on results labels for pipes. We have a couple of pipes that fall below our velocity limit, but as you recall, we specified a minimum pipe diameter, so that minimum diameter has been applied. The methods for representing household connections previously described are appropriate for steady-state analysis. If it is desired to run an extended period simulation or EPS, for example, an analysis over 10 hours, then there are some specialized nodes available which incorporate the volumetric data needed to calculate inflow, volume changes, and pump controls over time. These two nodes are the low pressure sewer or LPS tank and a holding tank. I'm going to display them simultaneously. These two nodes only differ in how the geometry for the tank is input, which also defines how the pumps are controlled. Remember, you can reference the device help to answer basic input questions. Both LPS and holding tank contain a pump with inputs for curve data here. Both nodes also have an inflow, which is assumed to be a steady rate of flow. If you want the inflow to vary over time, you can go to Devices, tank inflows, and specify a pattern number. Then, under Scenarios, Demand Patterns, you may input the factors in the selected row. The LPS tank defines the tank or basin with an equivalent diameter and a height. This height is the depth of the liquid above the bottom of the tank. For example, 4 feet. The pump will switch on when the liquid level reaches this value, and it will switch off when it drops to the elevation value, which is assumed to be the bottom of the tank. For a holding tank, the surface area is defined, and a high level and low level are input for the switching of the pump. These levels are elevations with reference to the same datum as elevation and grade. So the high value will be larger than or equal to the grade value, and the low level will be a value equal to or lower than the grade. To demonstrate extended period calculations, I'm going to load some completed models. To set up an extended period simulation, we would first need to go to Scenarios EPS, Extended Period Simulation. We have to check the Use EPS box, specify a total time, in this case 2 hours, and a computational time period. This is how often in hours that a calculation will be made. With low pressure sewer systems, sometimes these pumps cycle on and off fairly quickly, so shorter times with a smaller time period are acceptable. This model uses low pressure sewer tanks. I'm going to run the analysis, and we have the emphasis turned on, and we can see the devices that are running. If we step through the cases, we'll eventually come to a time when some of the tanks may be closed. If we click on an individual tank and display the results graph, we get a sense for the tank filling, the pump turning on, the pressure rises when the pump turns on, the tank becomes drained down to a lower level, and the pump kicks off. The tank begins to fill again, and the pump turns on. We can also see this dynamic by displaying flow rates. We can see the flow rates are positive when the pump is pumping, and 0 while the tank is filling. We're talking about the flow out of the sump through the pump, and when the pump is on, the flow rates are positive again. Here's an example with holding tanks. Again, we have inputs for high level and low level, which are elevations, and a surface area, and an inflow. We'll run the analysis, and we can see pumps cycling on and off based on the holding tank becoming filled.